Hi, today we're going to do FAQ 2008 number 3 for the Calc BC test. This is a Taylor series question and it gives us a table of values, which is really helpful because that means we don't have to calculate the values ourselves. So that was really nice. The first question, part A, is write the first degree Taylor polynomial for h about x equals 2 and use it to approximate h of 1.9. So to do this, we have the formula here of the series, and we're going to plug in n equals 0 and n equals 1 because we want to get till the first degree term. So that means x minus a, just x minus a. It's squared would be the second degree, so to the 1, that's why we have n going to 1. So for the first term, we find f0 prime of a, which is just f of a, and we want to use h, just regular h of 2, so that's 80. And then when you plug in 0, becomes 1, and 0 factorial is also 1, so this is just the first term. And the next term is we use f prime of a, so h prime of 2, it's 128. X minus a to the 1 is x minus a all over 1, because, this is 2 all over 1 because 1 factorial is 1. So this is our first degree Taylor polynomial, but the question also wants us to approximate h of 1.9. So to do this, we simply plug in 1.9 for x, and we get h of 1.9 equals 67.2. The second part of part A asks us, is this approximation greater than or less than the actual value? This we can determine by looking at the chart and finding h double prime of 2, which helps us determine the concavity. So since this number is positive, all the numbers are positive, that means it's concave up. So when we look at a graph, a concave up graph, any approximation that we do is going to be an underestimate, as we see here. So this is an underestimate as well. So in part A, we calculated the first degree Taylor polynomial. For part B, we're going to do the same thing, except we're going to add 2 more terms to find the third degree Taylor polynomial. To do this, we can go ahead and start off with the 2 terms we already found, which were 80 and 128 times x minus 2. For the next term, it's going to be positive since all the values in the table are positive. It's going to be n equals 2 because it goes 0, 1, 2, 3. And f double prime of a, that's h double prime of a, which is 488 over 3. And it's going to be x minus 2 to the n, and it's 2 squared all over 2 factorial. 2 factorial is just 2. And that's our third term. Our next term is going to be with n equals 3. H triple prime of 2 is 448 over 3 times x minus 2 to the n equals 3 cubed, and 3 factorial is 6. Now we're just going to simplify that. So we get 80 plus 128 plus 244 over 3 times x minus 2 squared plus 224 over 9 times x minus 2 cubed. And the last thing we have to do is plug in 1.9 for h, so we can use it to approximate h of 1.9. When we plug in 1.9 for x, we get 67.988. And that's our final answer for part B. For our final part, part C, the question is, use the Lagrange error bound to show that the third degree Taylor polynomial for h about x equals 2 approximates h of 1.9 with error less than 3 times 10 to the negative 4th. Okay, so the formula for Lagrange error is f n plus 1 prime of x times x minus a absolute value to the n plus 1 all over n plus 1 factorial. It's interesting to note that this formula is very similar to this formula, except it's just the next term. So I think that's significant because it shows that the error is just the next term. So that's a helpful way to remember the formula. So now we plug in values. So we want to bound to show that the third degree Taylor polynomial for h approximates. So we're going to plug in 3 for n. So when we plug in 3, we get f4 prime of x. So value x minus a is 1.9 to the 4th all over 4 factorial. And now we can look at the chart and plug in values. X is 2, so h4 prime of 2 is 584 over 9 times 2 minus 1.9 is 0.1 times 0.1 to the 4th all over 4 factorial. And calculating this gives us 2.70 times 10 to the negative 4th. And we know that this number is less than 3 times 10 to the negative 4. So we would just box this as our answer.